In this example, we're faced with the idea here of trying to design this truss. The truss, we know a couple things. One is that the load P, which is acting there at pin B, we know that that is something that will not exceed 50,000 newtons. The second thing is the material out of which we're going to make our legs has a different allowable stress and tension than it does in compression. In tension, it's 140 megapascals. In compression, it's only 85. So based on those two things, what we want to do is determine the required cross-sectional areas such that we don't exceed either the tension or the compression in the members that yield strength for that allowable load there of 50,000 newtons at P. We're going to do a joint analysis in order to first find the load carried by the members, and then from that we will calculate stress. But before we jump into that, what I want to do first is do a little bit of trig. I want to find the two angles that define this truss. So I'm going to be looking at finding the angle here of theta and the angle of phi. The angle of theta is E inverse tan of the opposite of this right triangle, which is H, divided by the adjacent, which is this length there of D. The angle phi. Inverse tan of opposite, which is H. Adjacent in this case, I'll get that right here, is B minus D. So we now know how to calculate theta and phi. Let's move down now and draw our FBD. Again, we're going to do the method of joints to find the loads carried by members 1, 2, and 3. We first look at the pin there at A. There's going to be a reaction of AX and AY. And I forgot to say that this is my X and this is my Y. And so at C, there's going to be a Y component, CY, and there's the applied force of P. The internal forces, I'm going to draw them all in tension. This way, what I will do is allow math to tell me in the end whether they really are in tension or in compression. So if I draw the force on A to the right, I got to draw the force on C to the left because of equal and opposite forces. This is F1, and then I have F2 shown before, and this is F3. This is the angle phi, as well as this one here. This was the angle of theta we found above. Theta is also this angle. I'm going to start at joint B. And I'm going to write down the equilibrium equation, the y direction for joint B. I got minus F2 sine theta minus F3 sine phi. For equilibrium, that is a 0. So from this, we see, of course, that F2 is of the opposite sine of F3, and then the ratio here is sine phi divided by sine theta times F3. I will now sum forces in X. Summing forces in X, I have the applied force P. I have minus F2 cosine theta. I have F3 cosine phi, that's in the positive X. And for equilibrium, that is a 0. So from this, if I substitute the equation before, this becomes P minus sine phi sine theta F3 times cosine phi, cosine of theta. And I have a minus, and a minus makes this a plus. and then I have F3 cosine phi. So from this, I have, it's strictly now in terms of F3. I can solve for F3. And what I get from F3 is going to be a P in the numerator. On the bottom, what I have is, looks like what I'm going to do is multiply through by, let's see here. I guess I have a cosine divided by a sine, so that's where I'm going with it. That becomes a cotangent. So this is sine phi cotangent of theta plus cosine phi, and there's a minus sign in front. The minus sign, of course, becomes important to us in just a bit in determining whether the stress is going to be tensile or compressive. So F2, from up here, you can see that F2 is going to be with a plus SI GN sign in front, sine phi divided by sine of theta, divided by sine phi cotangent theta plus cosine phi times P. And I think what I did here was that I got rid of my cotangent. This becomes sine phi divided by sine theta cosine phi plus cosine theta sine phi. So I just expanded out what the cotangent is. And this, from a trig identity, becomes sine of theta plus phi. So from this, I have a slightly simplified form of this expression, where F2 is going to be equal sine of the angle phi divided by sine of the sum of theta and phi as that times P. So this is our F2. And up here was our F3. And please note the F3 with a negative sign is in compression. F2 with our plus sign is in tension. Okay, we also need to know F1. So I'm going to look at joint C now. And when you sum forces acting in the x direction on C, you get minus F1 minus F3 cosine phi. For equilibrium, that becomes a 0. So F1 becomes a minus F3 cosine phi. So that becomes a P cosine phi divided by cosine phi plus sine phi cotangent of theta. And please note that that's a plus sign. So the conclusion we draw about segment 1 or element 1 is that it too is in tension. So 1 and 2 are in tension, 3 is in compression. That becomes important right now, because what we're going to do is look at link 1. The axial stress in there is the load F1 divided by A1. So from this A1 then, and keep in mind what we saw before is that this number was a plus. So A1, F1 divided by the allowable stress in tension. For member 2, this is sigma 2, is F2 over A2. This was positive. So again, we will be designing the area of member 2 based on that strength or the allowable stress here in terms of tension. And for member 3, sigma 3, which was F3 divided by A3, negative. So in this case, the area of that member is going to be, I'm sorry, I need to fix up this. I said F1, this should be F2. So this will be F3 divided by the allowable stress in compression. Please note 1 and 2 are based on allowable in tension, A3 allowable in compression. What did we do? Well, we need to find the loads carried by members 1, 2, and 3. We did a very standard truss analysis. I chose to do method of joints. You could have done method of sections. That approach is not that important, but in the end, make sure that whichever way that you do it, you're able to easily recognize whether the members are in tension or in compression. 1 and 2 in this case were in tension, so we designed based on the tensile allowable stress, whereas we found member 3 to be in compression, and we base that on the allowable compressive stress there of sigma c.